हम भी हमारे केमिस्ट्री में अपना पेपर पब्लिश कर सकते हैं 6.18 टाइप करते हैं
उसमें पानी है
खाली है इसलिए तो कह
तो वो अंदर रख दो बाद में बैठना मैं वहां से होके आता हूँ फिर एक तरह वेट 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 Hello, good afternoon, good evening.
Good evening, sir.
Kushbu, okay, I can.
Evening, sir.
Good evening, good evening. Okay, I'll share my screen now. We had completed up till this point, I suppose. Can anybody recall? We had done this separation of.
Yes, sir.
Okay, okay. So I'll just do a quick revision of what we did up till now. Uh, See, in this unit we have sampling, the process of sampling, how to sample a given uh, sample for analysis, and that should be a true representative of the bulk or the lot. That is what signifies sampling. And then once we have a true homogeneous representative of the bulk, we can go for applying a suitable sample preparation technique. And then we studied about some general steps in chemical analysis. There are about 7 8 steps which are common steps, which are general steps, which we use to analyze uh, any sample in any form. And after that, we moved on to the specifics of sample preparation, and under which we talked about liquid extraction or solvent extraction. We understood that it is basically extracting one analyte from a given sample into another phase which is immiscible with the original phase. And in solvent extraction, one phase is predominantly aqueous and the other phase is predominantly organic. It is used for separating inorganic substances or ions and organic substances as well. So both can be, extracted. It can be used for extracting the analyte of interest or analytes of interest. At the same time, it can be used to extract the unwanted substances from the analyte of interest, and as a result, it can it can be used either way, whether we extract the analyte of interest or we extract the unwanted components which are present in a given sample. And the second most important aspect of solvent extraction is that it is used for pre-concentration as well. And to understand uh, the the procedure of solvent extraction, we saw how a mixture of an acid and a base, or just a moment, I'll just one moment, just so I was telling you that we, as an example, as a representative example, we studied how a mixture of an acid and a base, or an acid or a neutral, or an acid and a phenol could be separated using this simple technique. And then finally, we just saw how a mixture of all four can be separated. All four can be separated uh, using different extraction mediums. Uh, when all four are together, acid, base, phenol, and neutral are all together, how it can be separated. So that is what I think we reached up till that point. Further, these are the conventional, glass apparatus which is being used for liquid extraction, and these are known as separatory funnels, which have a stopper, and then they have this knob which is made up of Teflon, whereby you can retain a liquid, or you can drain the liquid from these separatory funnels. The operation is very simple, and I suppose you all have used this glass apparatus at some point of time. And these are certain steps during liquid extraction using conventional separatory funnels. So one can easily pour the liquids through with the help of a funnel. So one can have both the phases together in this separatory funnel, keeping this knob closed here, And once we have added both the phases in this separatory funnel, we can stopper it. And then the next part is we need to shake this solution, this apparatus. So shaking is upside down, one can do, but in doing so, there is a lot of pressure generated, and therefore you can have this kind of an alignment to remove the pressure. Once you have shaken it for some time, then you simply invert it, and then release the pressure by opening this knob, keeping it inverted. And once that is done, again one can start with shaking the sample in a separatory funnel. So this is a simple process of doing separation using LLE. This is what is actually explained here. This extraction process can take about 2 minutes, 5 minutes, 10 minutes, depending upon the quantity present, depending upon the solubility, depending upon the suitable solvent system which we have selected as an extraction solvent, any specific organic solvent which we have selected. So we generally use this. But the main drawback of this separatory funnel is that, of course, you do it manually, one thing, and secondly, large volumes of organic solvents are being used here. So now looking at the environmental concerns, uh, this entire thing has been miniaturized into a very small vial, because these separatory funnels can take in about 20, 30, 40, 50 ml of liquid. So and then this is something, when you once the phases are separated, you have kept it for some time, and then when the layers are separated, one can drain the liquid. This liquid, there are two phases you can see. One is the aqueous phase, the other is the organic phase, depending upon the density of the solvent system which we have used. If it is lighter, organic phase would be here on the top and liquid would be here somewhere, and that this can be drained out using these conventional tubes, or in other cases where the organic solvent is denser. When it is denser, then of course it will be down, so it can be easily removed through this vent, and one can release it by opening this knob, and you can collect the fractions or the phases. And once you have collected the phases, the solvent can be evaporated to obtain the desired separated analyte or substance. Then I think we moved on to this, what is actually the need or what solvent extraction does, and that is, it is used to, as I said, isolate or separate the desired analyte, or it can be used to remove undesired components. That is also, either way, we are interested in separating the analyte of interest from a given sample. So it can be used to isolate or separate the desired analyte, or it can help to remove undesired components, unwanted components from the sample, leaving the analyte in the original phase or the aqueous phase. And the other most important part of solvent extraction is that it is used for pre-concentration. That means it is used to pre-concentrate the analyte of interest. And how it is done? It is done by simply taking in or extracting the analyte of interest in smaller volumes of organic phases, so that amount doesn't change, but the concentration changes. Because if you decrease the volume, concentration increases. So this is very important aspect of solvent extraction, that it is used for extraction plus pre-concentration. That is what is important to understand here. And then I suppose we just talked about different solvent systems which we are using in solvent extraction. The common solvents which are being used to extract are diethyl ether, toluene, hexane. These are some of the solvents which are water immiscible, and they are less dense than water. So they are on the top when we extract. Or else we can use chloroform, dichloromethane, carbon tetrachloride, or methyl tertiary butyl ether. These are some of the solvent systems which are denser, can be used for solvent extraction or liquid-liquid extraction. Having said that, one can also use a combination of solvents as well. One can also use combination of solvents, because this is important here. It is not that single solvent is used. There could be a combination of 2 or even 3 solvent systems. Even 3 solvent systems can be used here for extracting. So we generally have a extraction solvent system which comprises of 2 or 3 solvents in different ratios to extract a suitable analyte from a given sample. And as I said in the beginning, the phases are immiscible. One phase is predominantly water and the other phase is predominantly organic. Uh, I mean, this is what we understand, and because we know that all real samples are essentially present in aqueous medium. So that is how things move in solvent extraction. I think up to this point we just did it previously. Is there anything which one wants me to explain or જે ખબર નહીં પડ્યું કંઈક એવું છે? Anyone? Hello? Are you there?
Yes.
Okay.
Yes, sir.
Yes, sir.
Yeah. Okay. Okay. So I'll just move ahead. I just made a quick revision of what we did, and that is what I was, yeah, because there are three. I mean, there are few who have joined today, so just for the benefit of those, I just made a quick revision of what we did up till last time. Now in LLE, as I said, conventionally people used to use, and still it is being used at some places, we use separatory funnels for extraction. But now, because of environmental concerns, because of waste minimization of toxic organic diluents or solvents, we are now doing liquid extraction in very small vials, just like this, very small vials which have a capacity of 2, 3, 4, 5 ml. So the entire work is done in a very small volumes, and this is generally what is done. And secondly, it is not done manually. Now it is done automatically. There is a machine where we can put all these vials and we can have several such extractions simultaneously happening. So we can reduce use of organic solvents, one thing, and secondly it is not done manually, and this is how people now do liquid extraction. And the principle of liquid extraction is, of course, solubility, and this solubility therefore depends upon differential partitioning. This is important here. It depends upon differential partitioning. That means uh, because different analytes partition between two immiscible phases to a different extent. So differential partitioning between two immiscible phases is the fundamental basis of separation using liquid extraction. And the second most important point in liquid extraction is that we are always interested in separating the analyte in an unionized form. What does that mean? This means that when we extract anything from the aqueous phase to the organic phase, we know that ionic species do not exist in organic phase. They exist in polar aqueous phase. And to extract anything into an organic phase, there should not be any charge on that species. That means it should be unionized. And therefore, in liquid extraction, we basically create conditions such that the analytes which we are extracting should be somehow you neutralize the charge so that they are partitioned to a greater extent in the organic phase. So these two things are important when we study liquid extraction. Of course, we work with two immiscible solvents. Uh, the organic solvent can be a mixture of solvents. The fundamental basis of separation is differential partitioning, which depends upon the solubility, and yes, that we want that analyte should be in an unionized state. That is what we aspire, we we want when we do liquid extraction. There are different ways and means to do that. And at the same time, it can be used for, as I said in the beginning, it can be used for inorganic ions as well as organic molecules. So it can be used for both. For inorganic ions, you can very well argue that they have charged species. They are charged species. So how can they be extracted into organic phase? Of course, in those cases, we try to neutralize that charge. We create it into an unionized state. Organic substances, inherently being covalent in nature, this problem is relatively less. But even if it is there, one can always convert it into its neutral form or unionized state, so that one can have, greater partitioning between the two phases, and therefore one can have greater efficiency for extraction. Now this is, I think this is the slide where we stopped. I talked about this in my previous lecture. Pardon?
सर हमने ये कर लिया है।
अच्छा, ये कर लिया था. Okay, I'll just quickly go through this. When we distribute any analyte between two phases, this distribution is defined by some terms, and one such term is known as partition coefficient or distribution coefficient. These are the two terms which are being used to define the partitioning of this solute S between two phases, phase 1 and phase 2. And this sign indicates that there is an equilibrium, That means you will always find this is a dynamic state, and you always find some solute on the right and some solute on the left, such that you have an equilibrium constant. And this equilibrium constant is defined as the ratio of the activities of that solute in the two phases, or when it can be equated to be close to concentration of those species in the two phases. This is represented in square brackets. So the species is same, analyte is same, but this is phase 1 and this is phase 2. This is the phase 1 and this is the phase 2. And this is how it gets distributed. What we want is we want a greater value of K. That means we want greater concentration of our analyte in the extraction solvent, which is S2. Now there is a convention, as I said, that in the denominator we always represent the concentration in the aqueous phase, and in the numerator we use the concentration in the organic phase. This is a convention because in some cases the organic solvent is denser, and in some cases it is lighter than the aqueous phase. But whatever it may be the case, organic phase is taken here and aqueous phase is taken here as the phase 1. Aqueous phase is phase 1 and organic phase is S2. Then we moved on to calculate the extraction efficiency of any separation. Now for that, where are we heading now? We are heading towards some quantitative measures where we can find out how much is extracted and what is the efficiency of extraction. That is what we intend to move to understand now as we move ahead. So for that, what we intend to, we need an expression, we need a formula for sort of which can help us in calculating the efficiency of extraction. Of course, we want a higher value for K. Suppose that a solute S in volume V1 of solvent 1, that is aqueous. As I said, solvent 1 will be water, and solvent 2 in which we extract is an organic solvent. Here in this case, let it be toluene or hexane or any other solvent. And for the time being, let us assume that M be the moles of S, the analyte in the system. And when we extract, the fraction which remains in the aqueous phase, let us assume it to be Q. We know that the sum of total fractions is equal to 1. So if there is only one analyte in our sample and we are interested in extracting it to a different phase, then 1 minus Q would be the fraction which goes to the organic phase. If Q remains in the aqueous phase, then 1 minus Q goes to the organic phase. And to find out, so what we want to find out here is, as it is shown in this slide, we want a concentration of analyte in organic phase and concentration of analyte in the aqueous phase. So when we calculate concentration, we calculate concentration in molarity. So the molarity of the solute S, in phase 1 would be Q fraction of M moles divided by volume, because concentration is always with respect to volume. So you have this fraction of this moles divided by volume. This is your concentration in the aqueous phase. And for organic phase, the concentration would be 1 minus Q into M divided by V2, which is the organic phase. So we have the concentration of solute in the aqueous phase is this, and in the organic phase it is this. This is what we finally derive from this understanding. And if we substitute this in this equation which we had seen earlier, then it is something like this. And if we solve this equation with respect to Q, that is the fraction which remains in the aqueous phase, then the expression comes out to be finally like this. This is the expression here. Q is equal to V1 divided by V1 plus KV2. What is evident from this expression is that the fraction Q is independent of concentration. Fraction Q is independent of concentration, but it depends upon the volume of the aqueous phase, the volume of the organic phase, and the partition coefficient K. So fraction of any substance which remains in the aqueous phase is dependent on the volumes of the two phases and the partition coefficient, but is independent of concentration. This is important. It is independent of concentration. So this expression tells us this, Q. Now, if we do multiple extractions, और आपने assessment किया, this is known as one extraction. If you want to do second extraction, you keep that same original organic aqueous phase and add fresh organic phase. And then repeat the same process for that same time duration. This gives us the second extraction. So if you do two such extractions, this formula takes the form of Q square, because you have done it twice, and this becomes square of this entire term. And if you do this multiple times, 3, 4, 5, 6 times, then this expression can have a general like this expression, like Qn, this whole this whole thing raised to power n, and this helps us, this entire thing helps us in finding out the efficiency when we do a single extraction or when we do multiple extractions. So efficiency can be judged, can be assessed when we do the extraction once or when we do it multiple times, multiple batch extractions. This is what we understand through these expressions or formulas. I suppose we did this as well. I remember, I don't know whether I did it in GIE or HPP here, but we did this exercise, did we?
Yes, sir.
Yes. Okay. For the
Yes,
benefit
sir.
of, okay, good. Who was it? कौन बोला ये?
Sir, me, Richa.
Richa. Okay, Richa. Yes. Acha, you are following na up till this point. I'm going little slow in the beginning and I'm trying to repeat things just for the benefit of the students who were not present last time and who are new to this. But I think yes, this problem was done, and this problem essentially focuses on what we understood up till now, that what is the role of single extraction and what is the role of multiple extractions and how this impacts efficiency of extraction. So अब ये जो problem है वो कुछ ऐसे है कि solute A has a partition coefficient of 3, मतलब K value is 3, and when we look at this 100 ml of 0.01 molar aqueous solution of A, that means we have this as the V1, the volume of the aqueous phase. It contains this concentration, and we know that when we are finding out the fraction, it is independent of concentration. So this doesn't help us here. This doesn't help us here. So we are supposed to extract with an organic solvent an aqueous phase which is 100 ml and which contains some species which is the concentration of which is 0.01 molar. Now the question is, what fraction of A remains in the aqueous phase? What fraction of A remains in the aqueous phase when we perform one extraction? When we perform one extraction with 500 ml of organic phase, or when we perform 5 extractions each of 100 ml. So what would be the extraction efficiency? That is what we are supposed to understand through this problem. Now for this problem I have the solution as well. We know that Q is equal to V1 plus K into V2. V1 was 100. We know that. V2 was 500, part A. K was 3. Q was 0.062. And if you find out the percentage, it would be 6.2%. So 6.2% remains in the aqueous phase when the extraction was carried out with 500 ml of organic solvent, that is toluene. 94% gets extracted into the organic phase with 500 ml. Now the next is, what will happen if we do this extraction 5 times, but in each time we use 100 ml only? Now this is how the things change using this expression. What we find here is V1 remains constant, that is 100, 3 remains the same, but here now we have 100, but raised to the power 5 because we have done it 5 times, 5 extractions, and through which what we obtain here is 0.0098 fraction. If you multiply by 100, it becomes 0.098, which is approximately equal to 0.1%. What we understand from this is 99.9% gets extracted. Only 0.1% of that substance
remains in the aqueous phase. So that means it has greater efficiency, much higher efficiency than the previous case. And so it is what we infer from this is that when we do multiple extractions with small volumes, we get greater efficiency. We have used that same 500 ml, but in increments of 100 ml each for each extraction. And as a result, we get extraction 99.9%. So efficiency increases. I think up till this point we finished, and I suppose there are no questions up till now. Is there anything which you want me to repeat? Richa?
No, sir.
Okay, okay. Now, up till now, what we did was we were understanding how the analyte gets distributed between the two phases, and there we assumed that the analyte is in the neutral state. So we did not study anything regarding the charge analyte which might be present, because when we work with real samples, you don't always come across neutral species which we want to extract. There could be charged species as well. So there would be pH effects. There could be a case where the pH of that sample may not be 7. It could be maybe 9, or it could be 4, it could be 5, it could be 6, any pH of real samples. So there are chances that one can have species which are positively charged or which are negatively charged. So in those cases, what might happen is that the extraction efficiency may not be very good when we compare it with the neutral species which we just saw, because when it is a charged species, of course it will not go to the aqueous organic phase. It will try to remain in the aqueous phase. So there are chances that the efficiency might decrease. So under pH effects, what we'll study, under what conditions we can increase the extraction efficiency, what we can add, what we can optimize in our sample such that the efficiency remains the maximum possible. Now for this to realize, to understand, what we do here is we take a simple example. Now it goes like this. Consider an amine whose neutral form is B. Neutral form B, base B, has a partition coefficient K between aqueous and organic phase. Now its conjugate acid, base, agar base hai, it can readily take up protons. So there is a chance that if the pH is acidic, then this B might be converted into a form which is ionic, and that is BH plus. And when it is BH plus, come what may, it will not be extracted in the organic phase. So naturally, the entire B which we expect to be extracted may not be possible, and therefore the extraction efficiency decreases. So if we can come out with an expression which incorporates or which considers, takes into account the possibility of formation of ionic species just like BH plus in an acidic medium for a base. So there has to be some change in expression. That is what we will learn from this. Now, the moment we have the conjugate base of the conjugate acid for that base B, it will have a dissociation constant. It will have a dissociation constant. That means it will dissociate. It will dissociate. And because this is an acid, conjugate acid for that base B, so it will again have an equilibrium in that same system. And that is given by, which we all know, which is a very common expression, BH plus H3O plus gives B. If you add water to in aqueous phase, BH plus H2O gives B and H3O plus. This is a very fundamental expression for ionization constant for acids. So BH plus now is an acid, and therefore the equilibrium constant for this would be Ka, which is known as ionization constant. And that is given by a simple expression, K is equal to concentration of H plus ions into concentration of the base, the neutral base, and of course the ionic species, that is BH plus. Now this everything occurs or happens in the aqueous phase because it is an ionic species. देखो dissociation constant हम कभी organic solvent में नहीं निकालते. We always find out in an aqueous phase because aqueous phase में ionic species exist करती है. So this is one such expression which we find to happen in the aqueous phase when the pH is different, which is not neutral. To account for this, what we do is we do some change in our equilibrium constant, and that change is distribution ratio. So previously it was partition coefficient or distribution coefficient. Now it is distribution ratio, and distribution ratio D is given as the concentration, the total concentration of that same analyte or that base B in phase 2 divided by total concentration of that base in phase 1. Why we do this? In phase 2, of course, there will be only B because it is organic phase. But when we look at the aqueous phase, we will find, of course, base to some extent, and then we have BH plus also. So there are different species of that same substance, which we will find in the phase 1, which is the aqueous phase. And therefore, the equation for this would be something like this. The distribution ratio would then be equal to the concentration of base in the organic phase, this is B2, and the concentration of the base in the aqueous phase, this is B1. This is what we expect, but also we will find some concentration of BH plus as well. You see, if you just remove this BH plus here, it will be B2 divided by B1, which is as good as K. But just because of pH effects, what we find here is that we have another species in the aqueous phase because of acidic conditions. So to account for this, partition coefficient now gets converted into distribution ratio, and that is expressed by capital D. इतना समझ में आ रहा है ना? Richa and others?
Yes, yes, sir.
Okay, good. Now, to find out how distribution ratio and partition coefficient are related under pH effects, we can have an expression which has both these terms. These terms give us the same meaning, but they take into consideration two different aspects. One is for neutral species, the other accounts for neutral as well as the charged species, that is D. So now if we just simplify this equation by dividing this equation by say B1, each term by B1. So this will be B2 by B1. So this will be K. B1 by B1. So it will be 1. This will be 1. This will be K. And this will be BH plus divided by B1 square bracket. So we have K here, we have 1 here and plus this. Now BH plus divided by B1, the value for this can be found out using this expression of Ka, which we just saw in the previous slide. So if you just reform this equation to give an expression which is BH plus divided by B1, we will have something here to substitute in this BH plus upon B1. So and K, of course, we know is B2 by B1. So if we divide each term by B1, this is what we finally get. This is a very simple expression I've just written directly. One can easily sit and solve this. You will get this kind of an expression. Now what this tells us is that D, that is distribution ratio, is dependent upon the ionization constant. The ionization constant. What we understand here from this is that if H plus ions are more, D will be less. If H plus ions are more, D will be less. That means if the solution is an acid, acidic solution, and you have estimating base or separating base, naturally more base will be protonated. If more base will be protonated, less will be the distribution. If less will be the distribution, the D value would be less. The D value would be less. Just imagine if there is no pH effect, the equation becomes so simple. If you remove this, if H plus is very, very less, very less. So if it is less, you just remove it. What you find this expression K into Ka divided by K. You can cancel K, D becomes equal to K. So when under neutral conditions, when the H plus is very, very less, D becomes equal to K. But the moment H plus ions increase or the pH is lowered, D expression is given as K into Ka divided by K plus H plus. And this is a simple way of expressing this K. This is a different K from this K. These are different. And this entire you can have this thing. You can alpha. It is used this term. This is okay. I mean, just to simplify this equation. But this is what one should remember what is happening here. Now this is a figure which tells us that for a base, for an extraction of a base into organic solvent, what we want that the pH should be alkaline of that system. Now you can see if the pH is alkaline, what you find in the solution is only B, base intact B. But if you decrease the pH or increase the H plus ions, you find BH plus. So, and if you can see this figure, what it tells you is that at low pH, the D value or the log D value is less. But as you go on increasing the pH, the log D value increases, and then it stabilizes. It gives you a plateau that it remains constant. So beyond a particular pH, say around 10 around, the pH, the log D doesn't change. It remains constant. So from this figure, what we understand that to extract a base,
And to have a maximum efficiency of that base in extraction, we are supposed to create alkaline conditions. If they're acidic, make it alkaline, and once you make it alkaline, you can increase the D value, and more likely that this D would be very close to K. D cannot be greater than K. See, one thing is clear, D cannot be greater than K, always. It can be either same or less. So from this figure, for a base, for extracting a base, we can, from this equation, we can surmise that we need to keep an alkaline conditions for base to be extracted in an organic solvent. ये चीज समझ में आ गई? I don't know how many of you are getting me today, but I'll just ask, I'll take few names. Ankita Jadhav, do you understand? Khushbu, Harsh, Hetvi.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
okay.
Sir.
You are there. Good. Nidhi, and I can see Gopi. Okay, Patel Gopi. Uh, ठीक है. Okay, if you understand this, it is fine. And then after this, I have this slide. This slide is very simple in the sense that we were talking about base. Now, if we start talking about acid, then D value is equal to K into H plus divided by H plus plus Ka. So this is again a very simple expression which can be derived using that same thing. D is equal to concentration of Ha upon concentration of Ha in aqueous plus A negative, because if it is an acid, it will give you a negatively charged species. It will give you a negatively charged species when it dissociates. So Ha gives A negative plus H plus, this you are all aware of. So using that expression, if you substitute in this value in this equation D, you get this expression final, similar to the base which we just saw. For base, what we found out was this. For an acid, we found out this is the final expression for a weak acid. Now, with this backdrop, with this understanding, there is a problem which we can work out. This is the last thing which I'll do today. That how can we find out the partition, the extraction efficiency by changing the pH for a base. Now we'll just have a first look at what is the problem and what it seeks, what answers it seeks. The problem is like this. Suppose that the partition coefficient for an amine, that is base, is B, is K is equal to 3. Now when we say partition coefficient, that means it is assuming that the base is undissociated. The base is undissociated. And if it is undissociated, the K value is 3, and that is the maximum value which one has obtained. And the acid dissociation constant of BH plus. Of course, when we have a base, one can have under acidic conditions, one can have BH plus, and the dissociation constant of BH plus Ka is equal to 1 into 10 to the power minus 9. This much information is given. Now what is being asked? If 50 ml of 0.01 molar aqueous amine is extracted with 100 ml of solvent, so you can very well find out that V1 volume is 50 ml and the V2 volume is 100 ml. Now the question is, what will be the formal concentration remaining in the aqueous phase at pH 10 and at pH 8? So for a base, you already know that greater the pH, greater would be the efficiency, and lesser the pH, lower the pH, the efficiency would be less. And that is what is supposed to be proved using this problem. Now what it tells us is this. At pH 10 solution, when you look at solution part A, at pH 10, D is equal to, we know this expression we have just seen, K into K divided by K plus H plus. So if we substitute this into this expression, K is 3, partition coefficient under neutral conditions. Ka is 1 into 10 to the power minus 9, which is already given here. Then we have H plus. H plus is, since it is pH 10, the H plus would be 10 to the power minus 10. Therefore, we have pH 10. So we have very less H plus. And in that case, what D we find is 2.73. See, again, it is less than 3. As I said, D cannot be greater than 3. It can be 3 or less than 3. And here, because at pH 10, there would be some amount of very small fraction of your base would be dissociated, would have been formed, and therefore uh, the D value would be slightly less than 3. If there would have been no H plus, I mean the condition would have been H plus would have been 0, for example, then things would have been simple and D would have been directly equal to K. And now using D in place of K, the fraction remaining in the aqueous phase, because this is what we want, the fraction which remains in the aqueous phase is Q is equal to 50, that is volume of aqueous phase. This is also volume of aqueous phase. Now instead of K, we write D value. This is the only difference here. We want to find out what concentration remains or what fractions it remains. So instead of K, which is 3, but at pH 10, K is no more 3. K now becomes D, and D is 2.73. So if we do this, what we get is 0.15% is the fraction which remains, which is 15% if you multiply by 100. So 15% remains in the aqueous phase at pH 10 if we are extracting a base. 85% is extracted. That means 85% was neutral. 85% was neutral. B. That is why it couldn't go to the organic phase. And then what we found out was the concentration of amine, that 15% of this is this much. So this much concentration remains, and the remaining concentration, this is a bigger concentration, this is a smaller concentration. So only this much concentration remains. Now what will happen at pH 8? pH 8, there will be more protonation. And this is what is can be seen from this expression. It is 3. D is equal to, वो हम पहले D निकालते हैं. So D would be this into this 10 to power minus 9, that is Ka. But H plus ions is pH 8, so it would be 10 to the minus 8. So now the D value is 0.273 when the pH is 8. If we substitute this here, keeping everything constant here, 50, 50 and 100, 0.65 is the fraction which remains, which is equal to 65% remains in the aqueous phase. Only 35% has gone into the organic phase. So there is very little extraction as you bring down the pH. If you further bring down the pH to 6, there will be 80-90% which remains in the aqueous phase. Only 10-15% might go into the organic phase. So this is an example which tells us how the extraction efficiency changes for a base when we vary the pH. When we vary the pH, how the extraction efficiency changes. So if you have you understood this? I'll just repeat it again next time when we meet on Wednesday. but just to make you understand, this is a problem which requires some amount of understanding of how and when we use K and when to use D. Is it okay? I mean, have you followed this?
Yes, sir.
Okay, good, good, good. So if you have followed, and I'll just, did you have the previous lecture just now, 3 to 4? You had?
No, sir.
Oh no, I would have, otherwise I would have taken at 3 to 3 and.
No, sir.
Okay, okay. And what about 2 to 3? That was there, no?
Yes, sir.
Okay, वो हुआ था. Okay, okay, okay. ठीक है. So I'll just stop here. I'll just stop here, and I'll continue on Wednesday. Uh, you just think it over, this problem, and we will discuss this again if it is required. And let's take care, and till we meet again. Thank you for your presence.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.